The next two slides are going to be kind of quick because we're just going to run through some theorems that relate to circles. When we talk about the circles here, I've got this circle centered at A, and we're going to say that congruent central angles have congruent chords. So if I know that angle EAD, that central angle, and angle BAC, that central angle, if those two central angles are the same exact measurement, if they are congruent to each other, then I know the chords that are formed by those two central angles, so segment ED and segment CB, those are going to be congruent. So if your central angles are congruent, then you know the chords that are formed by those are also congruent. In the next theorem, it says that if you have congruent arcs, then you automatically know you should have congruent central angles. So if I know the measurement for arc ED and the measurement for arc CB are going to be the same exact measurement, or the arcs are congruent, I automatically know that the angles that are formed with those arcs, so the two central angles, angle DAE and angle BAC, those two angles are going to be congruent. So if the arcs are congruent, then the central angles are going to be congruent. The next theorem tells us that if you're working with congruent chords, then those chords should also have congruent arcs. So if I know that segment AB is congruent to segment CD, there should be a D down here. If I know these two segments are congruent, then I automatically know that the arcs that are formed by those chords are also congruent. So I would know that arc AB and arc CD would be congruent. So if the chords are congruent, then the arcs are going to be congruent. Testing that out, here's the example. They tell me that chord TV, that segment, is congruent to the chord SW or WS. If the chords are congruent, I know the arcs should be congruent. So I would just take the 9n minus 11 and set it equal to the 7n plus 11. When I do this, I'm going to subtract 7n from both sides. I get 2n, and I'm going to add 11 to both sides also at the same time, so it equals 22. Divide by your 2, you're going to get n is 11. Now that's not it, because I want to find the measure of your arc, WS. So WS is this one. So if I take the n and I throw it in, the measure of arc WS is going to be 7 times 11, which is 77, plus 11, which gives me 88 degrees. Now in this example, they're telling me that the two circles, circle C and circle J, are congruent, so they have congruent radii also. The other thing they're telling me is that the angle GCD and the angle NJM are congruent. So we got congruent central angles. We said in one of the previous theorems that if the angles, the central angles are congruent, then their chords are also congruent. That means that segment DG and segment NM are also going to be congruent. So if they're congruent, let's go ahead and set them equal to each other. So I would say 14t minus 26 equals 5t plus 1. If I subtract 5t from both sides, I get 9t minus 26 equals 1. I'm going to add 26 to both sides. 9t equals 27. And if I divide, t equals 3. So if t equals 3, the problem is they're asking for us to solve for nm. Take this 3, and we're going to throw it back in. So nm is going to equal 5 times 3 plus 1, which means that I get 15 plus 1. So my chord is 16 units long. Now the last two theorems in this section have to deal with the chords of circles. So if I'm dealing with a radius of a circle, CD here, and I know the radius, or even a diameter, is going to be perpendicular to a chord, what I know is that then forms two congruent parts. It bisects the chord, and it bisects the arc. So I would know that EX is congruent to XF, and I would even know that arc ED would be congruent to arc DF. So as soon as you're working with a radius, and you know the radius is perpendicular to a chord, it'll bisect the chord, and it'll bisect the arc also. The last theorem says that in a circle, the perpendicular bisector of a chord is going to be a radius. So you know what? If I know that I've got two congruent parts of a chord, and I know that it's perpendicular, I automatically know that this segment is going to be a radius or even a diameter. So let's go ahead and apply those two theorems to the following examples. In the first example here, they're telling me that we want to find out what NP is. So NP would be this whole entire distance here. So if this is the whole entire distance, and I know that from R to S it's 8, and from S to M it's 9, I see that I've got a perpendicular, and as soon as I've got a perpendicular, and we know that this is the center, so this is a radius, I automatically know that SN and PS are going to be congruent. It would be fantastic if I could figure out what the measurement of one of those was. So here's what's going to happen. I'm actually going to make a triangle out of this. So I'm going to go ahead and I am going to try to make a right triangle. I'm going to connect the center of my circle to the endpoint P. And when I do that, let me blow this up slightly. When I do that, I've got my right triangle. The R to my S was 8 units. It would be very, very helpful if I knew how much this amount was. So the R to the P, that is a radius. You know how much the radius of the circle is because you know the distance from R to M. That's a total of 17 units. So if I know from R to M is 17, I can put that on here. And if I want to find out what the distance from S to P is, all I have to do is use the Pythagorean theorem. So you're going to do x squared plus h squared equals 17 squared. If you know your Pythagorean triples, you already know that x would be 15. Otherwise, you can go ahead and figure that out by longhand. Otherwise, trust me on it, it is 15. So that means if the distance from S to P is 15 units, that's from here to here, that would mean that S to N is also 15 units. So the total distance from N to P would be 15 plus 15, so NP would be 30. Now that I've shown you an example, why don't you go ahead and try that one on your own? So you're going to find out what the length of QR is using the same exact setup. Pause the video, try it on your own, start it up when you're ready, and I'll have the answer written for you and I'll walk you through it. Taking a look at the last example here. We have the length from P to T is 10, from T to S is 10 also. Using that information, I know from P to S, the radius is going to be 20. So anywhere I draw a radius on this, it's going to be 20 units, meaning from P to R, that is going to be 20 units. So I drew my triangle out a little bit larger for you to see. Then I said, from P to T, that's 10. From P to R, that's 20. All I have to do is find the distance from R to T. So that's my x. So in Pythagorean theorem, I do x squared plus 10 squared equals 20 squared, because 20 was my hypotenuse, and I solved. I end up getting 17.32. I know that's the distance from T to R. I want to find then the distance from T to Q. Well, since it's a perpendicular radius to a chord, we automatically know that the distance from T to Q and T to R are the same. So if this is 17.32, that's going to be 17.32. You just add them up, or you could double your 17.32. And I run to the nearest tenth, and I ended up getting 34.6. Same process every time you're working with the radius and the chord. Follow those theorems along. If you have any questions on any of the information that was presented in the video, please make sure you write them down and you ask your teacher in class. Have a great night.